Okay guys, in this presentation I'm going to talk about temporal difference learning, and I'm going to cover the basics of temporal difference, how we can implement algorithms to estimate the value function using temporal difference, and in the end we are going to talk about the special methods or more popular methods of temporal difference, such as SARSA algorithm and the Q-learning algorithm, which are especially suited for intelligent control learning. I'm also going to compare the differences between dynamic programming, Monte Carlo methods, and temporal difference learning. So, temporal difference methods, bootstrap, and sample. So if you remember, dynamic programming is a bootstrapping method. So we estimate values based on other estimates. That's what we call bootstrap. And also in TD, in temporal difference, we sample, like in the case of Monte Carlo. That's why we say TD is like the best of dynamic programming and Monte Carlo. So bootstrapping is updating with an estimate of the value function. TD and DP bootstrap. Monte Carlo methods do not bootstrap. And in the case of sampling, which requires to make updates based on sampling, on interactions with the environment, we say that TD and MC methods sample. We need samples or episodes or actions performed. And DP, dynamic programming, does not sample. So we don't need to interact with the environment in dynamic programming. So this is a comparison between the learning rules between Monte Carlo methods up here and temporal difference methods down here. So if you notice here, the main measure of error is the subtraction or the difference between the final return. Remember that the final return is the sum of rewards. So you need to subtract from the final return the current estimate of the value of a specific state in time step t. That's in Monte Carlo. In the case of temporal difference, the very basic case, which is TD0, the error or the subtraction is from the reward that you will get in the next time step and the discounted value of the next state. Remember that this discount factor can be between 0 and 1. If we use gamma equals 1, we say that this is an undiscounted problem. So as you can see, the source of the error, the source of the change in the estimation of the value in TD will come from the reward that we will get in the next time step, versus Monte Carlo methods that the source of the change will come from the final return. So this is the very basic algorithm in TD0. This is the algorithm for calculating or estimating the value function in an MDP. So here we can see the reward plus gamma times the value of the next state. In this case, we're calling S prime the next state. And here you can see in color blue are the lines of code that would belong to the agent. The lines of code in green will be considered as part of the experiment program, and the lines in red will represent codes, lines of codes that will belong to the environment dynamics. So in this algorithm we have as input the policy pi to be evaluated. This initial policy could be just a random policy. Then we initialize the value function. This is a state value function, so we will have a value for each state. Usually we initialize this value function to be 0 for every state. And here in this notation, S belonging to S plus refers to the set of states that include the terminal states or goal states. That's the reason of the plus sign, that it includes the terminal states. Then we have a main loop here, which says repeat for each episode. You will initialize the state. Then you will repeat for each of the steps in the episode. So each step means each of the actions that you will execute during an episode. So you will select an action given by the policy that you are following for the current state S. Once you select the action, you execute that action, you observe what is the reward you will get, and you observe the next state, S prime. Once you have this reward and the next state, then you can apply the rule. So the value of the state where you were before executing the action, the state S, will take now the value of the current value of that state plus some alpha, some portion of this expression here, which is the reward plus gamma times the value of the next times the next state minus the value of the current or the previous state S. And once you have updated the value for that state, you will say, okay, now the current state S is going to be S prime. And you will repeat this until the state is terminal. So when you reach a terminal state, you have finished an episode. Then you will need to run this for many episodes. Here is a plot or a diagram to graphically or visually show what you do when you perform dynamic programming versus Monte Carlo versus temporal difference. So this first one is about dynamic programming. Remember, in dynamic programming, you need to use a policy function that will define a probability distribution over all the actions for each of the states. You will have a transition probability function that will tell you what is the probability that if you are in a current state ST and you apply an action A, you will move to a next state S prime. And of course we will have a reward and the value function that we are estimating. So when we apply these rules for a given state, in order to update the value of one state, we need to calculate all the possible next steps from that state. So we will consider every possible action that we can execute from that state. This is considered here in this sum for every A. And then we will consider for each of the actions what are the possible transitions. So when we apply the learning rule for dynamic programming, we need all this information to perform one single update of the value function for one state. If we observe what happens with Monte Carlo, in Monte Carlo we need to create an episode, a trajectory, until we have reached a terminal state. And once we have generated this episode, we go backwards and calculating the return from each of the states that you have visited. And you in each of these steps backwards, you keep updating the value for all of the states that you visited in each of the trajectories. Now, in the case of temporal difference, we don't need to calculate all the possible paths from that state, and we don't have to generate a complete episode. We just need to select an action, like for example following epsilon greedy. We perform that action and we observe what is the next state. And with this learning rule here, we can learn from this information. So as you can see, you can learn faster because you don't need as much information as you would need with dynamic programming or with Monte Carlo methods. Let's see an example. Consider this problem of driving home. So each day you drive home from your office. Your goal is to try and predict how long it will take at particular stages. When you leave office, you note the time, day, and other relevant info to try to calculate how much time you need to go to your home. Consider the policy evaluation or prediction task. So consider this example that you want to predict how much time you will need to drive from your office to your home. We will use this example to compare the difference between applying Monte Carlo to this problem or applying a temporal difference approach. So suppose that these are the times. Here on the left we see the different states of our MDP. So the first state is when you are still in the office and you are leaving the office. And this happens on Friday at 6. The next step would be that you reach your car, and when you reach your car you see that it is raining. Then the next state will be exiting a highway. Next state will be that you have reached a secondary road, but you are behind a truck. Then the next state will be entering your home street, so you're closer. And finally, the last state is, or the terminal state is, when you have arrived home. And these are the times. You start in time 0. This is the time that you predicted that you will need to get home. So you initially predict that you will need 30 minutes. And this is the predicted of the total time that it will take you to go home. So after leaving the office, you needed 5 minutes to walk to your car. But when you reach your car, you notice that it is raining, and then you update your prediction. So you say, okay, maybe because it is raining, I will go slower than what I thought, and then I will need still 35 minutes to get home. So the prediction now would be 40 minutes in total from the office to the home. 20 minutes after that, you are driving and you are exiting a highway, and then you predict that you will need 15 more minutes. So it have passed already 20 minutes and you predict 15 more minutes. So the total time now will be updated to only 35 minutes. Then 30 minutes after leaving the office, you are now in a secondary road, but you are behind a truck. And at that moment you predict that you will need 10 more minutes for a total number of 40 minutes to go home. You enter the street where you live, and it has passed already 40 minutes, and you think that you will need 3 more minutes to get home. So the total prediction now is 43, and at 43 exactly you arrive home, and then the time to go is 0. You have already arrived home, and the total prediction was 43. So we will consider this data and to see what is the difference between Monte Carlo and temporal difference. So suppose that for this exercise the reward going to be 1 per step. If we were minimizing travel time, what do you think would be a good reward? So if we want to minimize the time, then you could use, for example, -1 instead for every minute that you are waiting or you haven't arrived home. But there could be other ways to define the reward. So in this exercise, consider that you will count 1 per step. In this case, it is going to be on discounted problem, so gamma is going to be 1. In this exercise, G is going to be the time to go from a state T, or the state in time step T, and the value is going to be the expected time to get home from the current state in time step T. So the goal is to update the prediction of the total time leaving from office while you're driving home. With Monte Carlo, we would need to wait for a termination until we get home. Then we can calculate G for each step of episode, then apply our updates. So if we were going to apply Monte Carlo in this exercise, since we need the complete episode, which in this case, the complete episode involves getting home, and only then we can go back and update our estimates. And in the case of temporal difference, we don't have to wait until we reach home. Until we arrive at home, we can update our estimates after each of these states. So in this task, the rewards are going to be the difference in the minutes from going from one state to the next one. So it's the number of minutes that you needed to go from one state to the other. So that's going to be our reward. The value is going to be this column here, and this will be the values for each of the states. So how can we apply the temporal difference rule to update the values of these states? Suppose that the alpha that we are going to use is 1. So this alpha is going to be 1. We have here the learning rule, where we see again the reward and the gamma times the value of the next state. So if we are going to calculate the value of the office is this state here, the first state, the initial state. We will do it this way. The current value of office is 30. Okay, so here is going to be 30 and here is going to be 30. Alpha is going to be 1, gamma is going to be 1, to make it simple. The reward is going to be 5, because that's the time that you needed to go. That's the reward you got here. That's the time that you need to get to the next state. So for office, reward is 5, and the value of the state car is going to be 35. Okay, so you have here 35 minus 30, that's 5, plus 5 of the reward, that's 10. So our delta, our change in the new value of the office is going to be plus 10. So the new value of office, once we have applied this rule, is going to be 40. The same way you can calculate the value for the state car. So state car is the second state. So the current value of car is 35. So we will have 35 here, 35 here. The reward is going to be 15. Here is 15, and the next value is going to be 15. So we will have here 15 minus 30 minus 35, sorry, that's going to be 20 minus 20, and minus 20 plus 15, that's minus 5, sorry, and that's why the delta for car is going to be minus 5. So if the previous value was 35, 35 minus 5 is going to be 30. And we can do the same with exit. In exit we have the current value is 15, the next value is 10, and the reward is 10. So 10 minus 15 is minus 5. Minus 5 plus 10 is going to be 5. So the delta is plus 5. So if we had previously 15, 15 plus 5 is 20. So in other words, with temporal difference, after transitioning from one state to the other, we can update our estimate of the value of that state, which in this case is the total amount of time that you need to reach the final state. But if we compare that to Monte Carlo, we would need to wait until we have arrived home in order to update the times needed from each of the states. So that's basically an idea of why, or an explanation why temporal difference is better than Monte Carlo, in the sense that you can keep updating your estimates with less information. So advantages of temporal difference learning. TD methods do not require a model of the environment, only experience. Remember that in dynamic programming we do require a model of the environment. TD methods can be fully incremental, so we can make updates before knowing the final outcome, before knowing the return, the total return. It requires less memory because we just need to execute an action, and given the next state and the next reward, we can apply our learning rule. It also requires less peak computation, especially we compare it with Monte Carlo, because in Monte Carlo, once you have generated an episode, you have a lot of states that you need to update, and you need to do it at the same, not in the same time, but as soon as you have the whole episode, you need to update these values. So you will require more computation in that moment. You can learn without the final outcome. As we have seen, we just need one of the transitions, the corresponding reward and the corresponding next state, and that's all we need to apply the learning rule. Now, both Monte Carlo and temporal difference converge under certain assumptions that we will see next, but which is faster? Good question. So to keep analyzing this algorithm, consider this exercise or this experiment, which is a random walk. We have 5 states and we have 2 terminal states. So C is the start state. We will start moving in this state in the middle, in the center. This is considered episodic and undiscounted, so gamma is again 1. The policy is left or right with equal probability in all states, so we will have a probability of 0.5 to go left and 0.5 to go right from any of the states. The termination is at either of the ends, so these are these square states. Rewards are going to be +1 on right termination, so if we end up here, we will have a reward of +1, and in any other transition we will have always 0 of reward. So what does the real value function for this small problem is telling us? So since this is a very easy problem, we can calculate the value for each of the states. So for state A, the value of that is going to be 1/6. The value for B is going to be 2/6, and so on. The value for E, for example, is going to be 5/6. And we are going to approximate this using our temporal difference learning rule. So for this experiment, we are going to initialize the value for every state to be 0.5. And here is the result of the experiment. When you run this, for example, we initialize the algorithm, we initialize the values of each of the states to be 0.5. So for A is 0.5, for B is 0.5, and for every state is going to be 0.5. Okay, so we have this line here. After one iteration, the algorithm starts to make changes. So we have this change here. Only one of these states was changed. After 10 iterations, so after updating the value of 10 states, we have this line that is slightly in color blue. And after 100 iterations, we have a line that is closer to the true values of B, which is this line in red. So as you can see, this algorithm is able to approximate the real value of this problem of random walk. If we compare Monte Carlo versus temporal difference for this same problem, we see that the error that is generated by the temporal difference algorithms is smaller than the error that is generated by Monte Carlo methods. This plot was generated after 100 sequences of episodes. Okay, so in this experiment we can see that the results of both methods are different. Okay, and even using the same algorithm like TD, by changing alpha, you can get different results. So there is a way to implement these algorithms. This way is called batch updating. Batch updating consists in training completely on a finite amount of data. For example, you trained repeatedly on 10 episodes until convergence, and compute the updates according to TD or Monte Carlo, but only update estimates after each complete pass through the data. So the idea of batch updating is that you will have two variables in memory, one that is going to store the current value of each of the states, and another array that will store the new values for those states. So the idea is that you will be calculating the new values, but you are not going to replace the values, the old values for the states, but you are going to keep those values in memory. And after you have, for example, trained with 10 episodes or 5 episodes, then you update and you replace the old values of the states with the new values. That kind of training or implementation is called batch updating. And for any finite Markov prediction task that you implement these algorithms using batch updating, temporal difference converges if you use a sufficiently small alpha. Okay, and if you keep alpha constant, Monte Carlo also converges, but to a different answer. So it is important then to consider, in the case of temporal difference, to reduce the alpha. And in the case of Monte Carlo, you can keep a constant alpha, but the final result is going to be different from the temporal difference. And we are going to see an example of what is happening here, why these methods get to different results. After each new episode, all episodes seen so far are treated as batch. The growing batch is repeatedly processed by TD and MC until convergence, and this is repeated 100 times. So under the previous conditions of batch training and the different alphas, this is the final result of temporal difference, which is better than Monte Carlo methods. Okay, so under these circumstances, temporal difference is better than Monte Carlo. Let's see this example where we can see why these methods get to different results. Suppose that you have an MDP where you have only two states, state A and state B, and you have these observations. After visiting state A, you get a reward of 0, and you transition to state B, and after state B, you get a reward of 0. Okay, so this is, let's say, one episode that you observe. Then there's another episode with only one transition. You are in state B, and you get a reward of 1. And we have 1, 2, 3, 4 more, 5 more of these episodes that are exactly like this. You are in B and you get a reward of 1. You are in B and you get a reward of 1. And the last episode, you are in B and you get a reward of 0. So consider that each of these lines is a trajectory or an episode, and we need to estimate what is the value of state B and state A. So what value would you assign to B? One way to calculate this is saying, okay, after visiting 8 times, 1, 2, 3, 4, 5, 6, 7, 8 times B, 6 times out of 8 I got a 1 as a reward, and the remaining 2 times I got a 0. So you can calculate this to be 0.75. And what happens with state A? If we calculate it in the same way, we have visited only one time state A, and the reward was 0. So if we apply the same strategy to estimate the value of A, we will say that the reward or the value of A is 0. Okay, but there is another way to calculate this. However, this way to calculate it is the way that you will do it if you do or apply batch Monte Carlo. Okay, remember, in Monte Carlo you generate an episode. If you have this episode, what you would need to update the value of A would be to see, okay, what is the reward, the sum of rewards that I got after visiting A and reaching a terminal state. And the rewards here will be 0 plus 0, so you will get a reward of 0. And that's why the value for that would be 0 if you apply Monte Carlo. But what happens if you apply temporal difference? If you apply temporal difference, what you are doing is having this MDP. You are moving from state A, getting a reward of 0. You get into state B, and from B, sometimes you got a reward of 1. So this was 75% of the times, and 25% of the times you got a reward of 0, and then you reach the terminal state. So if you analyze this problem using temporal difference, then the value of A will be different, because from the only time that you transitioned from A to B, here you got a reward of 0, but you will take some portion of the value of the next state, which is this state B. So in the learning rule, remember, you have some gamma of the value of the next state, gamma times the value of S prime, and this value here is 0.75. So in this sense, the value of A will be also 0.75. And that is like the really powerful thing about these algorithms, that as a given state will inherit or will take a value based on its neighbors. So if A has a neighbor that has a larger or a large value, then A will have also a large value. Maybe it's not going to be exactly the same value than B, but it's going to be also large. But if A has had a neighborhood of states with small values, then A will also have small values.